Next question, if f of x is equal to x if x is less than 0, 1 when x is equal to 0 and x square when x is greater than 0, then evaluate limit extending to 0 f of x. So, we need to evaluate limit extending to 0 f of x, where f of x is given as x if x is less than 0, 1 if x is equal to 0 and x square if x is greater than 0. F of x is given as x if x is less than 0, 1 if x is equal to 0 and x square if x is greater than 0, and we need to evaluate limit extending to 0 f of x. Because this is piecewise defined function, let us evaluate limit extending to 0 plus and 0 minus separately. Let us first evaluate left hand limit. Limit extending to 0 f of x. As x tends to 0 minus, x is slightly smaller than 0, and when x is slightly smaller than 0, f of x is given by x. Whenever x is smaller than 0, f of x is given by x. So, this limit we can write it as limit extending to 0 minus x, which is 0. As x tends to 0 minus, x is 0. Similarly, let us evaluate right hand limit. Limit extending to 0 plus f of x is, as x tends to 0 plus, x is slightly greater than 0, and whenever x is slightly greater than 0, f of x is defined as x square. So, this limit would be limit extending to 0 plus x square, which is again 0. As x tends to 0 plus, x square also tends to 0. So, left hand limit and right hand limit are both equal to 0. So, the limit exists and is equal to 0. Limit exists and is equal to 0. Though the function is not continuous, f of 0 is not same as the limit value, but the limit at extending to 0 exists and it is 0. So, option is A. Next question, let f of x is equal to integral part of alpha plus beta sin x, where x belongs to 0 to pi and alpha is an integer, beta is a prime number, and we need to find the points of non-differentiability, the number of points at which f of x is not differentiable. It is given that f of x is equal to integral part of alpha plus beta sin x, where alpha is an integer and beta is a prime number, we need to find the number of points at which this function is non-differentiable in open 0 to pi. Now, because alpha is an integer, we can bring it out of integral part. F of x can be written as alpha plus greatest integer function of beta sin x. We all know sin x is continuous and differentiable function, and when x varies from 0 to pi, sin x will take all values from 0 to 1 and again through 0. Values of sin x from 0 to pi will vary from 0 to 1 to again 0. So, let us see, when will f of x be non-differentiable from 0 to 1? Whenever sin x is between 0 to 1, let us see what will be the points of non-differentiability of f of x. Now, whenever beta sin x is an integer, when sin x is varying from 0 to 1, beta sin x will vary from 0 to beta. 0 not included because it is open interval at 0, and 1 is included. So, beta sin x will take all values from 0 to beta. Beta is a prime number. So, in between, whenever beta sin x is an integer, f of x is bound to be non-differentiable. Whenever beta sin x is an integer, f of x is bound to be non-differentiable because of the discontinuity. So, let us see how many integers are there between 0 to beta. 1, 2, 3, so on up to beta. How many integers? There are beta integers from 0 to beta. So, whenever x is varying from 0 to pi by 2 included, here we have beta points of non-differentiability for the function f of x. Now, let us investigate from pi by 2 to pi. Because pi by 2 is already included in the discussion here, let me start my discussion from open interval pi by 2 to open interval pi. Beta sin x will take all values from, sin x is taking all values from 1 to 0. So, beta sin x will take all values from beta to 0. Beta is an integer, it is a prime number. How many integer points are there between beta to 0? At every point f of x will be non-differentiable. It is 1, 2, so on up to beta minus 1. So, there are beta minus 1 points of non-differentiability for the function f of x from pi by 2 to pi. So, altogether we can say there are beta plus beta minus 1, 2 beta minus 1 points of non-differentiability between 0 to pi for the function f of x is equal to integral part of alpha plus beta sin x. So, answer is 2 beta minus 1, which is option C. Next question, limit extending to n integral part of x plus integral part of x where n is an integer. We need to evaluate limit extending to n greatest integer part of x plus greatest integer part of x. Now, as x tends to n where n is given as an integer, we need to evaluate limit extending to n integral part of x plus integral part of x. So, let us evaluate left hand limit and right hand limit separately. For left hand limit, x is tending to n minus, that is x is slightly less than n, and when x is slightly less than n, integral part of x would be n minus 1. Integral part of x would be n minus 1. And because this is an integer, we can take it out of the integral part. This question can as well be written as limit x tending to n minus 1, limit x tending to n minus integral part of x plus take this integer out, integral part of x, which makes it 2 integral part of x. So, as x tends to n minus, x is slightly less than n, integral part of x would be n minus 1. Integral part of x would be n minus 1. So, this limit would be 2 into n minus 1. Now, let us evaluate right hand limit, limit extending to n plus greatest integral part of x plus this, we can bring it out, this is an integer, 2 integral part of x. So, right hand limit what would it be? X is slightly greater than n, x is slightly greater than n. So, integral part of x would be n. So, this is 2n. We can see RHL is 2n and LHL is 2 into n minus 1 for the limit extending to n, 2 into integral part of x. These two, because they are different, we can say limit does not exist, or the answer is option D. Next question, limit extending to 0, sin of x by m plus cos of 3x by m whole power 2m by x. We need to evaluate limit extending to 0, sin of x by m plus cos of 3x by m whole power 2m by x. Let us see this limit. As x tends to 0, we know x by m also tends to 0 and sin of x by m will tend to 0. So, this number is close to 0. 3x by m tends to 0. So, cos of 3x by m is close to 1. As x tends to 0, 2m by x is infinite, minus infinite, or plus or minus infinite depending on which side x is tending to. So, This is 1 power infinity form. Base is tending to 1, power is tending to infinity. It is 1 power infinity form. And every 1 power infinity form, limit extending to a f of x power g of x, we know we can write it as e power limit extending to a f of x minus 1, that is sin x by m plus cos 3x by m minus 1 into g of x. G of x is 2m by x, or we can write it as x by 2m. Instead of multiplying by 2m by x, we can divide by x by 2m. Now, let us see first part of the limit. This limit is e power limit extending to 0 sin x by m divided by x by 2m. Sin x by m divided by x by 2m. We can see as x tends to 0, x by 2m also tends to 0. Sin x by m is 1, and we have additional 2 here, which makes this 2, plus cos 3x by m minus 1 divided by x by m. Cos 3x by m minus 1, as x tends to 0, 3x by m is tending to 0. This is in the form cos theta minus 1 divided by theta square is half. So, cos theta minus 1 divided by theta, it will always tend to 0. So, this part of the limit, it will be tending to 0. So, we can write this limit as e power 2 plus 0, which is e square. So, answer for this question would be e square, which is option B. Next question, the function maximum of 1 minus x, 1 plus x, comma 2 is option A continuous at all points, option B differentiable at all points, option C continuous at all points except minus 1 and 1, and option D none of this. So, we need to check in this question continuity and differentiability of the function. Let us say f of x equal to maximum of 1 minus x, 1 plus x and 2. So, we have 3 functions. We need to compare these 3 functions, and maximum among the 3 would be f of x. So, for such type of questions, it is always apt to draw the graphs. Let us draw the graph of 1 minus x, 1 plus x and 2. 1 plus x, it is a straight line having y-intercept 1 and having slope 1. So, this is the graph of 1 plus x. 1 minus x is a straight line having y-intercept 1 and slope minus 1. So, this is the graph of 1 minus x. And 2 is a constant function parallel to x-axis. Now, f of x is defined as maximum of these 3 functions. So, the one which is above the remaining 2 will become f of x. Observe this region 1 minus x, 2 and 1 plus x. Among the 3, 1 minus x is maximum. So, f of x would not be 2, it would not be 1 plus x, it would be 1 minus x up to here. Then among the 3, maximum is 2 till here, and then among the 3, maximum is 1 plus x. So, now we can define f of x. 1 minus x when it becomes 2 is at x equal to minus 1. 1 plus x when it becomes 2 is at x equal to 1. Between minus 1 and 1, f of x is 2. When x is less than minus 1, f of x is 1 minus x. When x is greater than 1, f of x is 1 plus x. So, this is the graph of f of x. We can see, we can draw this graph without lifting the pen. So, this function is a continuous function, it is continuous at all points, and we have sharp points at x equal to minus 1 and x equal to 1. So, the function is not differentiable at minus 1 and plus 1. So, Answer for this question is the function is continuous at all points, which is answer A. Next question, evaluate limit extending to 0 1 by x into log of 1 plus ax by 1 minus bx. Evaluate limit extending to 0 1 by x into log of 1 plus ax by 1 minus bx. Log of a by b, we can see it as log a minus log b. So, this question can be written as limit extending to 0 log of 1 plus ax minus log of 1 minus bx divided by x. We are using the property of logarithm. Log a by b is log a minus log b. Now, we can see a standard limit here. Log of 1 plus ax divided by x is a. Log of 1 plus ax divided by x is a. We know log of 1 plus x by x is 1. 1 plus ax by x, we can multiply and divide by a, it becomes a. And similarly, log of 1 minus bx by x is minus b. Log of 1 minus bx by x is minus b. Now, we have one limit to be a and the other part to be minus b, and minus of minus b is plus b. So, our answer is a plus b, which is option C. Next question, limit n tending to infinity 3 power n plus 5 power n plus 7 power n whole power 1 by n. We need to evaluate limit n tending to infinity 3 power n plus 5 power n plus 7 power n whole power 1 by n. Observe, as n tends to infinity, 3 power n tends to infinity, 5 power n tends to infinity, and 7 power n tends to infinity. So, this is infinitely large number, and as n tends to infinity, power is tending to 0. This is in the form infinity power 0, which is an indeterminate form. This is in the form infinity power 0, which is an indeterminate form. So, it becomes difficult to directly evaluate this question. Infinity power 0 is a indeterminate form. So, what we need to do in this particular question is take 7 power n common from the base. This becomes n tending to infinity. When 7 power n comes out of this bracket, 7 power n power 1 by n, it makes it 7 into, this is 1 plus, from 5 power n we took 7 power n common, so this becomes 5 by 7 power n. From 3 power n we took 7 power n common, so this becomes 3 by 7 power n whole power 1 by n. Now, observe the question, as limit n tends to infinity, this is 1, 5 by 7 is a number smaller than 1, so 5 by 7 raised to the power n tends to infinity. A number smaller than 1, when it raised to infinitely large power, it becomes smaller and tends to 0. So, this number tends to 0. And again, as n tends to infinity, 3 by 7 is smaller than 1, 3 by 7 power n also tends to 0. Any number less than 1, when it is raised to infinitely large power, it will tend to 0. So, this base, it is now tending to 1. This is 1, 0, 0. Their sum would be tending to 1. 1 power n something close to 0 will always be 1. Anything power 0 is 1, and 1 power 0 will also be 1. So, this limit would be 7 into 1, 7. So, answer for this question is 7, which is option D. Next question, let h of x is equal to minimum of x and x square for every real number x. Then we need to check whether option A, h is continuous for all x, option B, h is differentiable for all x, option C, h dash x is 1 for all x greater than or equal to 1, and option D, h is not differentiable at x is equal to minus 1. For the function h of x is equal to minimum of x and x square we need to check whether h is continuous for all x or it is differentiable for all x, or h dash x if it is 1 for all x greater than or equal to 1, or f if it is not differentiable at x equal to minus 1. Again, to check continuity and differentiability of this function, let us plot the graph of this function. F of x, h of x is minimum of x and x square. So, draw the graph of x. It is a straight line passing through origin and having slope 1. X square, quadratic, parabolic in nature, vertex at origin. X and x square intersect each other at the point 1 comma 1. Now we have to see which one is minimum among the two. The one which is below will be minimum among the two. In this region, we can see x square is above x. So, minimum of the two would be x, not x square. So, h of x is x, up to x is 0. Again from 0 to 1, we can observe x square is below x. So, minimum of the two is x square, not x. Again from 1, x is below x square. So, h of x will be x, not x square. So, this is the graph of h of x. From minus infinity to 0, h of x is x. From 0 to 1, h of x is x square. From 1 to infinity, h of x is again x. Now, we can see we can draw this graph without lifting the pen. So, we can simply say the function is continuous. The function is continuous at all points. And again, coming to differentiability, it is non-differentiable at 0. We can see a sharp point here. Left hand derivative at this point, slope of this line is 1. Right hand derivative at this point, tangent at vertex for x square is 0. So, right hand derivative is different from left hand derivative. So, the function is not differentiable at 0 and again not differentiable at 1. We have sharp points here. So, the function is not differentiable at 0 and 1, differentiable elsewhere. For all h greater than or equal to 1, h dash x is equal to 1. That is true. That is true for all x greater than 1, but not for x greater than or equal to 1. At 1, we have a point of non-differentiability. And at x is equal to minus 1, the function is very much differentiable and derivative is equal to 1. So, among the options, it is only option A. The function is continuous for all x. Answer is option A. Next question. Which of the following functions have finite number of points of discontinuity? Which of the following functions have finite number of points of discontinuity? Option A, tan x. Option B, x into integral part of x. Option C, mod x by x. And option D, sine of integral part of n pi x. Sine of integral part of n pi x. So, we have to investigate these functions. A tan x, B x into integral part of x, C mod x by x, D sine of integral part of n pi x. For the sake of the question, we can directly say its answer C, because mod x by x is discontinuous at x equal to 0 and continuous elsewhere. Mod x is continuous on R, x is continuous on R. Their ratio would be continuous provided denominator is not 0 and denominator is 0 when x is 0. So, except for x equal to 0, it is continuous at every point. So, it has only one point of discontinuity which is not in its domain, that is x equal to 0. Let us also try to understand why it is not option A. We all know the graph of tan x. Tan x is discontinuous at every odd multiple of pi by 2. Tan x is discontinuous at every odd multiple of pi by 2. So, there are infinitely many odd multiples of pi by 2. So, there are infinitely many points of discontinuity for the function tan x. Coming to B, differentiability of x into integral part of x is very interesting. At any integer, left hand derivative, limit extending to n minus, let us check differentiability at any integer n, limit extending to n minus x into integral part of x, f of x, minus f of n is n into integral part of n is also n square divided by x minus n. When x is smaller than n, integral part of x would be n minus 1. So, this is x into n minus 1. This can be written as x into n minus 1, or I can separate out xn minus x square minus x. Now, we can see x minus n gets cancelled here. This limit is limit extending to n minus x minus n gets cancelled. We are left with n minus x by x minus n, x by x minus n. As x tends to n, x minus n tends to 0 and numerator is non-zero. So, this ratio it's going to be infinitely large unless and until x is 0. So, at all integers other than 0, this function is non-differentiable, left hand derivative does not exist. So, we again have infinitely many points of discontinuities for the function x into integral part of x. So, that is again not part of our answer. Similarly, at every integer, whenever x is an integer, whenever n pi x is an integer, sign of integral part of n pi x will be non-differentiable. So, again we have infinitely many points of non-differentiability for the function sin of integral part of n pi x. So, only option is mod x by x, answer C. Next question, evaluate limit extending to 2 minus 1 par integral part of x. Evaluate limit extending to 2 minus 1 par integral part of x. So, as x tends to 2, we need to look at the behavior of the function minus 1 par integral part of x. Let us evaluate left hand limit and right hand limit separately. Left hand limit, as x tends to 2 minus, x is slightly smaller than 2, and when x is slightly smaller than 2, integral part of x is 1. So, this will be minus 1 par 1, which is minus 1. And in the right hand limit, x tends to 2 plus, as x is slightly greater than 2, integral part of x is 2. So, this is minus 1 par 2, which is 1. We can see left hand limit differs from right hand limit. So, the limit does not exist, or answer is among the available options it is none of this. Limit does not exist, answer D. Next question, the value of f of 0, find the value of f of 0 so that the function f of x is equal to 2x minus sin inverse x divided by 2x plus tan inverse x is continuous at each point in its domain. We want the function f of x is equal to 2x minus sin inverse x divided by 2x plus tan inverse x to be continuous in each and every point in its domain. For that, we need to find the value of f of 0. We know tan inverse x is continuous on R, sin inverse x is continuous in its domain, 2x is continuous in its domain, 2x is continuous in its domain. So, this function is continuous in its domain unless denominator is 0, and denominator is 0 for x equal to 0, which is not part of the domain. So, let us separately find the value of f of 0. So, for the function to be continuous at 0, limit extending to 0 f of x, that is limit extending to 0 2x minus sin inverse x divided by 2x plus tan inverse x. This needs to be equal to f of 0. Now, let us evaluate this particular limit. We all know limit extending to 0 sin x by x is 1. Limit extending to 0 sin x by x is 1. So, limit extending to 0 x by sin x is also 1, and from that we can say limit extending to 0 sin inverse x by x will also be 1. That is because graph of sin inverse x is image of graph of sin x with respect to the line y is equal to x. Graph of sin inverse x is image of graph of sin x with respect to the line y is equal to x. So, sin x by x is equal to 1 in the vicinity of 0 implies sin x and x are almost same. And when sin x and x are almost same, its image of sin x, sin inverse x will almost be same as x. So, limit extending to 0 sin inverse x by x is 1, and similarly limit extending to 0 tan inverse x by x will also be 1. So, let me divide numerator and denominator by x. We have discussed that this number is 1, this is also tending to 1. So, our answer will be 2 minus 1 by 2 plus 1, 1 by 3. So, f of 0 has to be 1 by 3 for the function to be continuous in its domain. Its answer B. Next question, evaluate limit extending to 0 1 plus sin x minus cos x plus log of 1 minus x divided by x cube. We need to evaluate limit extending to 0 1 plus sin x minus cos x plus log of 1 minus x divided by x cube. We can do this question either by power series expansions or by L'Hospital rule. So, in this, let us do it by L'Hospital rule. As x tends to 0, cos x tends to 1, 1 minus cos x is 0, sin x is 0, log 1 is 0, x cube is 0. So, this is 0 by 0 form, and in 0 by 0 form, limit extending to a f of x by g of x, we know it is equal to limit extending to a f dash x, derivative of numerator by derivative of denominator. So, let us differentiate denominator 3x square, derivative of numerator, derivative of 1 is 0, derivative of sin x is cos x, derivative of minus cos x is sin x, and derivative of log of 1 minus x is minus 1 by 1 minus x. So, we need to evaluate limit extending to 0 cos x plus sin x minus 1 by 1 minus x divided by 3x square. Let us apply L'Hospital rule again, as this is 0 by 0 form again, as x tends to 0, cos x is 1, sin x is 0, 1 by 1 minus 0 is 1, 1 gets cancelled, it is 0, and denominator is also 0, 0 by 0 form. Again applying L'Hospital rule, it is limit extending to 0, derivative of cos x is minus sin x, derivative of sin x is cos x minus 1 by 1 minus x whole square, derivative of 1 by 1 minus x is minus 1 by 1 minus x whole square into minus 1, which makes it 1 by 1 minus x whole square, divided by denominator derivative is 6x. Now, we can see some standard limits. Sin x by x we know it is 1. So, we have minus sin x by 6x, which will be minus 1 by 6. So, this part of the limit, it is minus 1 by 6 plus, let me add subtract 1 here, minus 1 plus 1 cos x minus 1 by x square, we know it is minus half. So, cos x minus 1 by only x, this will tend to 0. So, this part of the limit is 0. So, we can as well erase cos x minus 1. So, we have next part of the limit to be limit extending to 0, 1 minus 1 by 1 minus x whole square divided by 6x. Or we can also write this as 1 minus x whole power minus 2. X is a very small number tending to 0, and whenever x is very small, 1 plus x whole power n will be approximately 1 plus nx. And when x is tending to 0, we can happily replace 1 minus x whole power minus 2 with 1 plus 2x. This 1 minus x whole power minus 2 can be happily replaced with 1 plus 2x. 1 and 1 gets cancelled. So, we are left with minus 2x in the numerator. Minus 2x divided by 6x is minus 1 by 3. So, our limit is minus 1 by 6 minus 1 by 3, which is minus 1 by 2. Answer is option B. Next question. If f of x is equal to sine of e power x minus 2 minus 1 divided by log x minus 1, then evaluate limit extending to 2 f of x. F of x is given to be sine of e power x minus 2 minus 1 divided by log x minus 1, and we need to evaluate limit extending to 2 f of x. Now, let us see the nature of the function in the neighborhood of 2. As x tends to 2, x minus 2 tends to 0, e power x minus 2 is 1, 1 minus 1 is 0. So, this is sine of a number tending to 0. As x tends to 2, log of x minus 1 tends to 1, log of x minus 1 tends to 0. So, this is again a 0 by 0 form. We can either evaluate it directly or we can go for L'Hospital rule. So, let us evaluate it directly. Let us convert this limit into limit extending to 0. Limit extending to a f of x. We are investigating the nature of f of x in the neighborhood of a. So, this limit will be same as limit extending to 0 f of a plus x. Limit extending to a f of x, the quantity inside f is tending to a, and in limit extending to 0 f of a plus x, as x tends to 0, quantity inside f is again tending to a. So, these two limits are one and the same. Whenever we want to convert a limit extending to a to form limit extending to 0, this is a very useful identity. So, let us convert this limit into limit extending to 0 format. This will be limit extending to 0, replace x with a plus x, replace x with a plus x, sine of e power, replace x with x plus 2, 2 and 2 gets cancelled, we have e power x minus 1 divided by log of, replace x with x plus 2, x plus 2 minus 1 is 1 plus x. As x tends to 0, e power x minus 1 by x is 1. So, e power x minus 1 is equivalent to x. This we can replace it by x. Log of 1 plus x by x is also 1. So, log of 1 plus x can be replaced by x. And sin x by x we know it is 1. So, answer for this question would be 1, which is option C. Next question. Evaluate limit extending to a cos x minus cos a by cot x minus cot a. Evaluate limit extending to a cos x minus cos a by cot x minus cot a. This question We can again do it either by L'Hospital rule, it is 0 by 0 format. As x tends to a, cos x tends to cos a minus cos a is 0 by 0 format. We can do it by L'Hospital rule, or we can do it by simplifying the denominator. Cot x can be written as cos x by sin x, cot a can be written as cos a by sin a. Take LCM. In the numerator, apply transformations. You can see a factor of sin of x minus a by 2 getting cancelled, and then you have answer for this question. So, for this session, let us do it by L'Hospital rule. Limit extending to a, because this is 0 by 0 format, let us differentiate the numerator. Derivative of cos x is minus sin x. Cos a is a constant, its derivative is 0. Derivative of cot x is minus cosecant square x, and derivative of cot a is 0. Cosecant square x in the denominator goes up and becomes sin square x. Minus sign and minus sign we can cancel. So, sin cube x as x tends to a is sin cube a. So, answer for this question is sin cube a, which is option A. Next question, f of x plus y is equal to f of x into f of y for all xy belonging to R. If f of 3 is 3 and f dash 0 is 11, then find the value of f dash of 3. In this question, we are given a functional relation f of x plus y is equal to f of x into f of y for all xy belonging to R. And it is also given that f of 3 is 3 and f dash 0 is 11, and we are asked the value of f dash of 3. Usually for such questions, students have a tendency to partially differentiate the functional relation, but nowhere in the question it is mentioned that the function is differentiable. So, never ever approach such questions by partial differentiation. We need to evaluate f dash of 3. F dash of 3 by definition we know limit h tending to 0 f of 3 plus h minus f of 3 divided by h. F dash x we know it is limit h tending to 0 f of x plus h minus f of x divided by h. This is limit h tending to 0 f of 3 plus h. Use the functional relation given f of x plus y is f of x into f of y. So, f of 3 plus h is f of 3 into f of h, or f of 3 which is 3, we can take it common, 3 into f of 3 we have taken common. So, we are left with f of h minus 1 divided by h. Now, let us see what is speciality of the limit h tending to 0 f of h minus 1 by h. Substitute x and y to be 0. F of 0 is equal to f of 0 into f of 0, or f of 0 whole square. F of 0 can't be 0 because that makes the function identically 0, whereas f dash 0 is given to be 11. So, f of 0 has to be 1. F of 0 has to be 1. F of 0 is equal to f of 0 whole square. That leaves us with two possibilities, f of x equal to f of 0 equal to 0 or f of 0 equal to 1. F of 0 can't be 0, but because that makes identically the entire function 0. So, f of 0 is 1. So, this 1 we can write it as f of 0. Now, observe limit h tending to 0 f of h minus f of 0 by h minus 0 is f dash of 0. This is the definition of f dash of 0. Observe the limit h tending to 0 f of h minus f of 0 divided by h, this will be f dash 0. So, this is 3 times of f dash 0 and f dash 0 is given to be 11. So, answer will be 33. Answer is 33, which is option A. Next question, evaluate limit extending to 0 1 plus tan x by 1 plus sin x whole power cosecant x. Evaluate limit extending to 0 1 plus tan x by 1 plus sin x whole power cosecant x. Observe the function as extends to 0. As extends to 0, tan x tends to 0 and sin x tends to 0. So, numerator is 1, denominator is 1, making the ratio 1. And as extends to 0, we all know cosecant x tends to infinity or minus infinity based on x is tending to 0 minus or 0 plus. So, this is 1 power infinity form. And in every 1 power infinity form, we write limit extending to a f of x power g of x as e power limit extending to a, it is 0 in this case, f of x minus 1, 1 plus tan x by 1 plus sin x minus 1 into g of x, which is into cosecant x or 1 by sin x. Now, let us look at the difference. 1 and 1 get cancelled. This is e power limit extending to 0 tan x minus sin x divided by sin x into 1 plus sin x. Observe as extends to 0, 1 plus sin x tends to 1, 1 plus sin x tends to 1. So, from the product we can remove this 1 plus sin x. Tan x is sin x by cos x. We can see one sin x common throughout, we can cancel it. So, cancelling that sin x, we will be left with 1 here and this will be secant x. So, our limit is limit extending to 0 secant x minus 1, which is 0. So, this is e power 0 1. Answer for this question is 1, which is option B. Next question, if the function f of x is equal to x plus 1 power cot x is continuous at x equal to 0, then f of 0 is 0 or f of 0 is e, or option C f of 0 is 1 by e, option D none of this. So, in the question we are asked to find the value of f of 0 given that f of x is continuous at x equal to 0. F of x is defined as x plus 1 whole power cot x, and it is given that this function is continuous at x equal to 0. For if the function is continuous at x equal to 0, limit extending to 0 x plus 1 power cot x should be equal to f of 0. Limit extending to 0 x plus 1 power cot x should be equal to f of 0. Observe this limit as extends to 0, x plus 1 is 1, cot x is infinitely large. This is 1 power infinity form, and 1 power infinity form we can write it as e power limit extending to a, that is 0 in this case, f of x minus 1, x plus 1 minus 1 is x, into g of x is into cot x, or I can also write this as divided by tan x. Instead of multiplying by cot x, we can divide by tan x. And this is an elementary limit, limit extending to 0 x by tan x is 1. So, our answer is E, which is option B. Next question, let f of x is equal to a into modulus of x square minus x minus 2 divided by 2 plus x minus x square if x is less than 2, b if x is equal to 2, and x minus integral part of x divided by x minus 2 if x is greater than 2. F of x is defined as a into modulus of x square minus x minus 2 divided by 2 plus x minus x square if x is less than 2, b if x is equal to 2, and x minus integral part of x divided by x minus 2 if x is greater than 2. We are asked to find the values of a and b given the function is continuous at 2. It is given that the function is continuous at 2 and we are supposed to find the values of a and b. For the function to be continuous at 2, f of 2 should be same as left hand limit at 2 should be same as right hand limit at 2. Let us observe right hand limit at 2, limit extending to 2 plus whenever x is slightly greater than 2, f of x we know it is given by x minus integral part of x divided by x minus 2. Here x is just greater than 2, slightly greater than 2. So, integral part of x would be 2. So, this limit is 1. Right hand limit we have it to be 1. So, value of b f of 2 should also be 1. B should be 1. Now, let us look at left hand limit. Left hand limit should also be 1 for the function to be continuous at 2. Left hand limit is limit x tending to 2 minus, and whenever x is less than 2, f of x is given by a into modulus of x square minus x minus 2 divided by 2 plus x minus x square. Now, in order to remove this modulus, we need to know whether x square minus x minus 2 is positive or negative. So, let us factorize x square minus x minus 2. X square minus x minus 2 is x minus 2 into x plus 1. X minus 2 into x plus 1. And this is minus of x minus 2 into x plus 1. Minus of x minus 2 into x plus 1. Now, x is slightly less than 2. So, x minus 2 is negative. X plus 2 is positive. So, that makes the product negative. X minus 2 into x plus 1 is negative, and modulus of a negative number is minus of that number. So, x minus 2, x minus 2, x plus 1 gets cancelled, minus sign gets cancelled. Left hand limit is a. Left hand limit is a. And for the function to be continuous, a should be equal to b should be equal to 1. So, its answer B. Next question, let f maps R to R be a differentiable function and f of 1 is equal to 4. Then evaluate limit extending to 1 integral of 4 to f of x 2t dt by x minus 1. We need to evaluate limit extending to 1 integral of 4 to f of x 2t dt by x minus 1, and it is given that f of 1 is 4, and it is also given in the function that f is a differentiable function. F is a differentiable function. Now, observe the integral. In this integral, we are integrating with respect to the variable t. So, x minus 1 is independent of the variable. We can bring x minus 1 always out of the integral. So, this limit we can write it as limit extending to 1 integral 4 to f of x 2t dt whole divided by x minus 1. As extends to 1, upper limit would be f of 1 and f of 1 is given to be 4. So, integral 4 to 4 is a point integral which comes out to be 0. So, numerator is tending to 0, denominator is tending to 0, this is 0 by 0 form, and in order to evaluate this 0 by 0 form, let us go for Newton-Leibniz rule and also L'Hospital rule. L'Hospital rule says that this limit it is equal to limit extending to 1 derivative of numerator divided by derivative of denominator. Derivative of denominator is 1, and in order to find derivative of numerator, let us use Newton-Leibniz theorem, which says derivative of a definite integral is derivative of the upper limit f dash of x into substitute upper limit in place of t 2f of x minus derivative of lower limit 0 into whatever is 0. So, our limit is now limit extending to 1 f dash of x into 2 into f of x. So, as x tends to 1, f of x tends to f of 1, which is 4. So, this number is 8. 8 into f dash of 1 will be our answer. So, answer is 8 into f dash of 1, which is answer A. Next question, find the value of f of 0 so that the function f of x is equal to root over a square minus ax plus x square minus root over a square plus ax plus x square divided by root a plus x minus root a minus x becomes continuous for all x. Becomes continuous for all x. So, because the function is given to be continuous for all x, the function should also be continuous at 0. And for the function to be continuous at 0, limit extending to 0 f of x is root over a square minus ax plus x square minus root over a square plus ax plus x square divided by root over a plus x minus root over a minus x. Root over a plus x minus root over a minus x. This limit, it should be equal to f of 0. So, our target is in evaluating this limit. To evaluate this limit, rationalize denominator and rationalize numerator. So, multiply by root over a plus x plus root over a minus x in both denominator as well as numerator. So, we have to multiply by root over a plus x plus root over a minus x. In denominator it is a minus b into a plus b, which is a square minus b square, which is a plus x minus a minus x. A and a gets cancelled. This is 2x. So, when we rationalize, denominator becomes 2x. And also observe, as x tends to 0, this is root a and this is root a. So, the sum becomes 2 root a. We can write this as 2 root a outside the limit. Let us similarly rationalize the denominator. To rationalize the denominator, we have to multiply and divide by root over a square minus ax plus x square plus root over a square plus ax plus x square, and in the numerator it is of form a minus b into a plus b, which is a square minus b square, which is a square minus ax plus x square minus a square plus ax plus x square, a square and x square we can see they get cancelled, and minus ax is minus 2ax. So, numerator is as simple as minus 2ax, of which 2x gets cancelled and we are left with minus a, and this minus a can be written outside the limit. And as x tends to 0, these two quantities are 0, 0, root a square is a, we have 1 by 2a, and that 1 by 2a gets cancelled with this 2a, and answer is minus root a. So, answer would be minus root a, which is answer B.